Okay, so now I really am pleased to introduce Ali Raza. Now, Ali is a PhD student at Boston University also, and also Red Hat research intern. And he's going to talk today about how he is turning the Linux kernel into a unikernel. Unikernels are single address space operating systems. This makes it possible to actually turn existing unmodified Linux applications into unikernels, which is really exciting. And Ali is beginning to run experiments now to understand, what performance improvements this brings for different applications. And we're also looking. He's also looking at micro benchmarks and micro optimizations of syscalls, particularly with the Memcache D application, but with others to come. So with that, I'm really happy to introduce Ali Raza.
Finally, let's start. Hi all. As Rich introduced me and the project, I am Ali Raza, and today I'll be talking about Unikernel Linux. I'm a PhD student at Boston University, working with Professor Oran Krieger, and I'm also a research intern at Red Hat, working with some very smart people whose name you can see on the screen. So let's start by discussing if we or why we need specialized operating systems like unikernels, and talk about what they are and what might be holding them back. So the structure of today's general purpose operating systems is not suitable for a number of today's key use cases. In the cloud, client workloads are typically run inside dedicated virtual machines. A general purpose operating system designed to multiplex resources among many user processes is instead being replicated across many single user and often single process virtual machine. So a general purpose OS running a single application workload. Also, applications that require high performance I/O use the frameworks like DPDK and SPDK to actually bypass the kernel and gain unimpeded access to hardware devices. So the general purpose operating system is actually coming in the way of performance sensitive workloads. Clearly, for some use cases, the general purpose operating system is too general purpose, and there is a need for specialized operating systems, which are optimized for each workload. And in response to these questions, recently there has been a resurgence of research exploring the idea of library operating systems or unikernels. So what are unikernels? As Richard already said, in a unikernel, an application is statically linked with a specialized kernel, and it is deployed directly on hardware, which might be physical, might be virtual. An application runs in a single address space with the kernel and other user libraries. There's no separation between the operating system and the application privilege levels. Unikernels have shown to be small and lightweight as compared to normal kernels. They allow application-specific optimizations. There are many unikernels already developed, for example, EBRT, IncludeOS, MirageOS, etc. And when compared with Linux, these unikernels have demonstrated significant advantages in boot time, security, resource utilization, I/O performance, etc. Unfortunately, despite tremendous advantages, unikernels have not achieved widespread adoption. One might find the reason for this in how these unikernels are developed. For example, some of them are developed from scratch. Others are developed by forking an already existing code base and stripping it down to create a small, lightweight, specialized kernel. In both of these approaches, the result is a separate code base, which then needs to be maintained. This new code, in most cases, is not well tested, especially if you compare it with Linux. It's not well tested at all. These unikernels don't have sufficient functionality to run broad class of applications, and mostly are limited to only virtualized environments. They do not support accelerators, for example, GPUs and FPGAs, which are fundamental for modern high-performance applications. And most of them often only run on a single processor core. So also, perhaps the most concerning reason is that no unikernel has attracted a large community of developers. making it increasingly unlikely that these challenges will be addressed anytime soon. So let's talk about the unikernel we've been working on and how is it different from other unikernels. UKL, as the name suggests, is a Linux kernel config option to build the Linux kernel as a unikernel. As you already know, Linux already has a huge community around it, and its code base is mature and well tested. We don't want to maintain a separate code base, as I already said. And the only way UKL can be successful is if the community maintains it and improves it incrementally over time, the same development model that Linux has. So all of this motivation made sense to us, but one big question remained: is it even possible? Can we do it with minimal code changes so that potentially in the future these changes can be accepted upstream? Building a unikernel as part of Linux, what performance advantages will we get, if any? Will we be able to do application-specific optimizations that other unikernels have shown? So we decided to give it a try, and it turns out that it is possible that we have been able to, it is possible, and we have been able to get a functional unikernel. The number of lines changed is small, and we feel it's relatively non-intrusive changes to normal kernel functionality. So let's talk a little bit about the implementation without going too much into details. We use the kernel build process to create the unikernel, which means we have to modify the VM Linux linking step to include compiled application and user libraries. So we compile the application, we compile the user libraries, we don't link them, and we use the kernel build process. And in the linking step of the kernel, where VM Linux is linked together, we add these user compiled object files, and then everything is linked together into a final VM Linux binary. Since the application and kernel code is statically linked together in VM Linux binary, we have to modify the kernel linker script to add sections which are not normally present in the kernel, but are present in user code, for example, the thread local storage section. Once the kernel boots up, it calls execve to create the first user space process. That's how the kernel normally works. In UKL, there is no separate user space, and there's no separate user elf file to be loaded into memory. And execve needs a user elf file to actually load into memory. But we cannot just do away with the execve call. It is extremely important because it properly sets up the task struct, the struct, and the stack, etc. It sets all of these things up properly. So what we did was we modified the execve call slightly to run without any elf file. So it does not need to now parse or load any user elf, and it sets up all the structs and stack properly. We do specify the entry point into the application code. So once the execve call finishes, we can jump into that entry point. And as you all know, because we're using glibc, the entry point is _start function. We ensure that there is no ring transition ever. This means that when the application invokes kernel functionality, we don't use syscall or sysret instructions. Also, during interrupts and faults, we ensure that the IRET happens to the same privilege level as the kernel. So either we are returning from an execve call, we are returning from what used to be a syscall, we're returning from faults, interrupts, whatever, we stay in the same privilege level as the kernel. So since application and user libraries, including glibc, have to link with the kernel, they have to be compiled with custom build flags. Most important is the MC model equal to kernel flag. There are a couple of other, there's one other flag actually, which is no red zone. And I can talk about that later. We modified the glibc macros, which are used to do syscalls. For example, the inline syscall macro and friends. So now instead of doing a syscall instruction, we call the kernel entry point directly. We don't modify the register setup in any way, so that everything just works out of the box. For example, the syscall number goes into the RAX register still. This allows the kernel to service the syscall. I'm still calling it a syscall, but it's not a syscall now. So this allows the kernel to service that functionality without any modification. We do have one slight modification because the syscall instruction wants its fourth argument to be in the R10 register, whereas a normal call instruction wants its fourth argument to be in the RCX register. So we do make that small change. Once the kernel jumps to _start, glibc initialization happens. For example, where the stack alignment takes place and the setup of the thread local storage section takes place. TLS section has to be copied from the original ELF for every thread. Normally, glibc parses the application ELF and finds where the TLS section is, and then copies that over for every thread that it creates. In UKL, as you know, there is no separate application ELF. So we define variables in the kernel linker script to mark the start and end of the TLS sections. We modify glibc initialization slightly to use these symbols and get the TLS initialization image from there. So we've created a few different flavors of UKL, and we are trying to currently study the effects of each of these on different workloads. So the first one is the most is the simplest one, which switches to a kernel stack whenever executing kernel code. So you invoke some kernel functionality, which used to be a syscall earlier. You go through the kernel entry point. You normally, as it happens normally as well, you change to a kernel stack. You service that functionality. You come back, switch again to user stack, and that's it. So there's that simple version. Then there's the version where we remain on user stack throughout, even when executing kernel code. Another one that we're experimenting with is where we bypass the kernel entry and exit code when invoking kernel functionality. So as you all know, whenever we enter or exit the kernel, be it a syscall, be it a fault handling, be it interrupt, if we're coming from user space, we have to run kernel entry code, and on our way back, we have to run kernel exit code. This code, as you know, is responsible for a lot of different things, including the RCU stuff. It is responsible for scheduling the user threads, if the scheduling thread scheduling flag is set, so on and so forth. So we need to run this, but there is overhead attached to running this functionality every time. So we have a flag now where you, for the performance sensitive parts of the application, you can just turn this off and you directly go to the kernel functionality, do the kernel functionality and come back without having to pay the overhead for entry and exit. And once you are out of the application's performance sensitive part, you can then turn these on and normal functionality would resume. As you can see on your screens, the number of line changes from Linux is minimal, around 550 at max from normal Linux. And all the changes in glibc are also minimal, and they are limited to a separate subdirectory inside the glibc tree, so that all the changes are basically separate from the rest of the glibc code. So I'll talk about, so there were many interesting challenges we had to fix in getting this unikernel to be functional, and I'll just discuss a few of them. Kernel entry and exit points, as I've already discussed these. Although we remain in kernel mode, we still have to run the kernel entry and exit code when we enter and exit the kernel respectively. And this is paramount for correct functionality, as I already discussed. But normally, in the normal Linux, not in Unikernel, in normal Linux, Linux first checks if the access came from user mode or if the return is to user mode, and only then runs these functions. But there are no such transitions in UKL, but we still need to run these functions for correctness. So what we did was we created a per thread variable. As soon as we find ourselves in kernel entry point, be it syscall, interrupt, or fault handling, we first check this variable. If this says user mode, we run that kernel entry code, we save this on the stack and change that variable. So now it specifies that it is now in kernel mode. This helps because during nested interrupts, if we get interrupted while we are in kernel mode, we don't run the entry code because we check this variable and see, oh, now we are in kernel mode. On return, we check the variable which we saved on the stack. If it says that now I am returning to user mode, we run the kernel exit code and change the value of the variable back to specify that we are now in user mode, and then we do an iret. And just to be clear, no string transitions happen. Page faults. If we run out of user stack, we get a page fault. That's normal. Normally, on a page fault, we automatically switch to a kernel stack, so we service the page fault and return. That's what happens normally in Linux. But in UKL, since we are in the same privilege level all the time, no automatic stack switch happens in case of a page fault. So page fault happens, you're still on the same stack. So imagine we have a page fault for the stack extension, but we don't change to a kernel stack. We don't have any more stack left to actually service that fault. So what happens? Double fault. So we fix this through the interrupt stack table. This is a mechanism, as you all know, through which we can specify up to 7 per CPU exception stacks. Some of these stacks are used by Linux already. For example, for the debugging, for non-maskable interrupts, for double faults, etc. We specify another one for page faults and update the IDT entry for page faults to specify this stack index. So this way, every time a page fault occurs, we always jump to the stack, and here we service the page fault and then return. This is actually very interesting, and we spent a long time actually figuring out what's happening here. The kernel does not expect stack page faults while running kernel code because it assumes that you're on a kernel stack, and kernel stacks don't fault. But in some flavors of UKL, as you know, there are cases where we don't switch stack while executing kernel code, and it is possible to get stack-related page faults while in kernel code. And this can result in undefined behavior, including deadlocks. So imagine we are in some memory management code. For example, we are in an mmap code and have taken a write lock on the read-write semaphore of the mm struct. This means that we are actually modifying the list of VMAs in some way. So if at this point we suffer a stack page fault, we go to the fault handling code. Here, normally what happens, we try to take a read lock on the mm struct semaphore without realizing that we already have the write lock on it. So the read lock fails. At this point, unable to get the read lock and unable to proceed, we mark ourselves as uninterruptible and wait for someone to give up the write lock so we can be woken up. But since we are the ones having the write lock, this results in a deadlock. So this was solved by a brilliant idea by Larry Woodman. So what he suggested and what we did was that in the page fault handling code, we only want to take a read lock on the semaphore to walk the list of VMAs and find out the VMA to which the faulting address belongs. In our case, deadlock is only caused by a stack page fault when you are in kernel. And we know that, and if somehow we know the stack VMA beforehand, we don't have to take this read lock anymore. We don't have to walk this list of VMAs. We already know the VMA. So what we did was we created, when a thread is created, we save its stack VMA in a per thread variable. In case of a page fault, we first check if the faulting address belongs to this VMA. If yes, we know that it is a stack page fault and we don't take the read lock. We just use this VMA and we service the fault normally. And problem solved, we don't try to take a lock and there is no deadlock then. So as Richard said at the start of this presentation that we are only now beginning to run experiments. So I've added a little result of Memcache D. So this shows Memcache D running normally on Linux, and also the same Memcache D totally unmodified, compiled as different versions of UKL. All instances are running inside QEMU KVM on 6 cores, while the client runs on a different physical machine. So this graph shows 99th percentile tail latency and also shows a black line, which is the 500 microsecond SLA line. And in order to understand this graph, you want to understand that we want to service as many queries per second as possible while remaining under the 500 microsecond SLA. So as you can see that the green line is doing better than the red and yellow lines, which are doing better than the blue line. So the syscall bypass is doing best, and then the two other flavors of ukill, and finally normal Linux. But this result should only be right now interpreted as a proof of functionality. We should not look at the numbers right now. We should only see this and say, okay, it is possible to run a non-trivial application with UKL. Right now, we cannot basically take these numbers right now as they are, because we need better virtualized network, high-speed virtualized network to get repeatable numbers without noise. Right now, there's a lot of noise in these experiments. We need to run this bare metal to get even better numbers. But at least this shows that UKL can, as I said, run unmodified applications, and there's performance benefits to be had. So what's the way forward? We need to run micro benchmarks to test different things. For example, the syscall level functionality, and see what the performance benefit or no benefit is there for different syscalls. We need to run Memcache D, as I said, with high-speed virtual network and bare metal. We need to get reproducible results and attribute. We should be able to attribute performance differences to actual reasons. And in order to do that, we need to get perf to work inside UKL to understand any performance differences. But we are now at a very interesting stage. We are ready to explore many research questions. We expect UKL to perform better than vanilla Linux, but not as good as custom unikernels written from scratch. But would that really be the case? Will we see that? Can we surpass Linux in terms of performance, boot time, memory footprint, etc.? And if we can, it would be so interesting to see where all these gains are coming from. Is it due to not doing the ring transition every time? Or is it due to statically compiling everything? Or is it due to a non-preemptible versus a preemptible kernel? Or something else? So we are at a very interesting stage. We have all these questions, and we are now at a stage where we are going to do the experiments and see the results and understand what's happening. And we have the opportunity now to run different optimizations, for example, the link time optimization and the profile-driven optimization, and see what benefit we can get there. We can also replicate the research done by other unikernels and see if we get similar benefits. And there's a ton of interesting research questions that we are really excited to explore. So this is it from me. I'll be happy to take your questions.
Thanks, Ali. I think that's a really fantastic talk. I mean, the thing that really stands out to me there is the small, the 550, whatever it was, lines of code changed in Linux. I mean, that's absolutely fantastic. It makes it so much easier to get this stuff upstream, give it a sort of long-term future. So if you really do have questions, I think we should now move us into the sessions part of this, because of course there's another talk following straight after this. So with that, yeah, thanks everyone. I'm going to hand it over to Hugh now.